Hello students. In our previous video lecture, we have discussed about the significance of slip, and also we have seen what do you mean by slip speed, and also we have seen the dependence of rotor parameters on the value of the slip. As soon as the rotor starts rotating, we know that the slip value changes. At starting, the slip value is 1. When the rotor is stationary, the slip value is 1. And as soon as the rotor starts rotating, the value of the slip changes. And accordingly, we have seen that all the parameters of the rotor, especially if you talk about the induced voltage, E2, then if we talk about the standstill reactance, the value of the reactance, so reactance value also changes. Why? Because the reactance value is 2 pi f into x into L, sorry. So obviously reactance depends on the frequency, and we know that as soon as the rotor starts rotating, the rotor frequency changes. So since that rotor frequency changes, the reactance also changes, and hence and also the induced voltage, that is E2, induced voltage on the rotor side, that also changes as soon as the rotor starts rotating. So we've already seen all those, how does it changes and what are the effects, how does the power factor changes as soon as the rotor starts rotating. Now today, lecture in today's lecture basically will continue with the rotor structure. When we'll draw some, we'll derive few things, or we will focus on few things so that we are able to draw the equivalent circuit of an induction machine. Now we know that in an induction machine, we have already discussed that the value of the induced EMF is nothing but that is equal to, we have seen that E induced EMF is equal to root 2 pi f into phi into n into kW, where we know that this kW is nothing but winding factor, then phi is flux per pole, then n is the number of turns, f is the supply frequency. This is the basically this is the formula of induced EMF, which we have already derived in our class lectures. So now in today's lecture, I'll be concentrating more on the correlation, on the relation between, you can say, the transformer and an induction machine. So basically, if you talk about the equivalent circuit now, so the transformer and the induction machine resembles each other. Means that the equivalent circuit of a transformer somehow is very similar to an induction machine. Induction machine and transformer have a similar equivalent circuit. Now we'll talk about how. See, we know that in a transformer there are basically two windings. One is primary winding, another is secondary winding, and there is a core connecting these primary winding and secondary winding. That core is basically a core of magnetic material having high permeability. But and similarly, in an induction motor also we have two windings. One is placed on the stator, that is known as stator winding, and other is placed on the rotor, that is known as a rotor winding. And those two windings are separated by some air gap. In that transformer there was no air gap. In fact, there was a magnetic core. But in an induction machine, instead there is an air gap. Okay, this is you keep on noticing these small minor variations, differences between induction machine and a transformer. Also, in an induction machine, we have seen that there is a factor. See this thing, kW1. What is kW? KW is nothing but winding factor, and we've already discussed in detail that winding factor is nothing but it is a product of your distribution factor and your pitch factor. But in a transformer, there is nothing like this thing, kW. Why? Because in a transformer, the windings are concentrated. There is nothing called distributed winding transformer. Means windings are concentrated, and hence the role of this thing is not much prominent in transformer, if you can say. So now in a transformer, what do we do? Uh, we basically use a transformer for either stepping up your voltage or stepping down your voltage. Okay, so in a transformer, E1 divided by E2, if you say the primary side voltage in a transformer is E1, and the secondary side voltage in a transformer is E2, then E1 divided by E2 is nothing but that is equal to your turns ratio, which is given by N1 divided by N2. Similarly, if we talk about this ratio, E1 divided by E2 at starting, look at this. at starting. Why I'm talking about starting? Because at starting we know that the rotor is stationary, and if the rotor is stationary, we know that the value of the slip is nothing but equal to 1. Okay, so this ratio E1 divided by E2 at S equals to 1 for an induction motor is Kw1 into N1 divided by Kw2 into N2, where E1 is nothing but the induced voltage in the stator winding, E2 is the induced voltage in the rotor winding at slip equals to S equals to 1. So if you talk about S equals to 1, then this ratio is equal to Kw1 into N1 divided by Kw2 into N2. Why? Because at S equals to 1, the frequency of the rotor is also F, and the frequency of the stator is, as usual, it is always F. So by remaining terms, and flux per pole, we know that flux per pole remains the same for stator as well as for rotor. So this is how basically we are getting this ratio, and we know that this Kw1 into N1 is again a constant, and Kw2 into N2 is again a constant, and the ratio of these two things is again a constant. We can denote it by some letters, say A. So this is, so now you can see that at standstill, or when the rotor is stationary, this is the thing we are getting. E1 divided by E2 is equal to some stationary turns ratio. So can you see the resemblance? So this actually is behaving like a transformer. If the value of the say is, if say that the value of A is 2, then E1 is equal to twice of E2. You can say that this is acting as if a step down transformer, since the secondary side voltage, that is E2, is only E1 divided by 2. So it is acting as if as a step down transformer, right? Remember one thing very carefully, that right now I'm talking about the situation when the rotor is stationary. See, the scenario will change when rotor starts rotating. Okay, we'll see how, but keep this in mind. Okay. See, in a transformer, what actually is happening is that in a transformer we know that we are stepping up the voltage or stepping down the voltage, but one thing remains constant in a transformer, and that is the frequency. In a transformer, the primary side frequency is equal to the secondary side frequency. There is no change in frequency, which is very important point, and you should be very careful about this thing. Why? Because when we talk about this induction machine, we know that the primary side frequency, that is the stator frequency, is always the same, always the supply frequency. But the secondary side frequency, that is the rotor frequency, depends on the slip. As soon as the rotor starts rotating, the slip starts changing, and if the slip starts changing, then the rotor frequency starts changing. Now here the difference comes. Okay, we'll see about these things, but right now I want you to understand the induction machine when it is stationary. When the rotor is stationary, we'll try to correlate between the transformer equivalent circuit and the induction motor equivalent circuit. When the rotor is stationary, that means when the slip is 1, you can see here at S equals to 1, Fr equals to F, that means the frequency of the rotor is equal to supply frequency. So that is why they are saying that as S equals to 1, this is just like a transformer. Now this is the equivalent circuit. You can see it is exactly the same as that was in a transformer. See, you can see this side represents the primary side of the transformer. And what is the primary side of an induction machine? Primary side of an induction machine is nothing but the stator, where you provide the external supply. This V1 is nothing but the external supply which we have provided. R1, as these things we have already discussed. R1 is nothing but the per phase stator resistance. X1 is nothing but per phase stator leakage reactance. This Xm magnetizing reactance. Okay, now this represents your rotor structure. This is E2 induced voltage in the rotor winding. R2 rotor internal per phase rotor resistance, and per phase rotor leakage reactance. Okay, now this is you also remember one thing, that this is leakage reactance of the rotor at standstill. This value will change. Now what are the various changes which will occur as soon as rotor starts rotating? With these values, E2, X2, frequency of the rotor, these all values will start changing, and thus this equivalent circuit of the rotor, which will start changing as soon as the rotor starts rotating. So here comes the differences between the equivalent circuit. Now, but right now we are talking about the situation when the system is stationary. Okay? See, they have also written one thing that R1 and X1 is obviously very small because the winding resistance and the leakage reactance, we want this to be much smaller. But then they are saying that, see, the XM is much greater than R1 and XM. That is, of course, magnetizing reactance. But I'll tell you one thing, that the magnetizing current in an induction machine is much larger than the magnetizing current in a transformer. Why is it so? Because we know that in an induction machine there is an air gap, and if there is an air gap, then there obviously the reluctance will be much larger. While in a transformer, instead of an air gap, there is actually a magnetic core, whose reluctance will be much lower. And hence, in order to produce the same flux, the mmf required, the current required, the magnetizing current required in a transformer, in a induction machine, will be much larger than that in a transformer. So always keep this in mind, that in a transformer, the magnetizing reactance, the magnetizing current required is much larger than that in a transformer. This thing should be very clear. Okay. And hence, we know that the magnetizing current in a induction machine, it is, we are drawing this magnetizing current at lagging power factor. So much very low power factor. Induction machine is operating at a very low power factor, since such a huge amount of magnetizing current it is withdrawing. Now we can, one thing is also there, I have not written in this PDF, but you can write, I'm telling it verbally, that in a transformer, you must have studied that in a transformer the no load current is 2 to 4%. Very small current. No load is very small current. Why? Because no load, there is a very small resistances and all that, and means reactance and all those things are very, reactance of XM of a transformer is larger. But in an induction machine, this no load current is very high. It is around 25 to 40%, you can see. This is very high of the rated value. While in a transformer, it is only 2 to 4% of the rated value. That's why we keep on ignoring that part. That's why we were shifting that parallel path and all those things. I'll not go into that detail, but I'll suggest you to go back and see the equivalent circuit and study the equivalent circuit of a transformer, so that you will get a much more and very proper insight of this topic, and you'll be able to correlate much better, in a better way. Okay. So now we are talking that, see, in this line I've written that there's a mistake. The induction machine value of XM is much higher. Instead, it should be much lower than that of a XM in transformer. So see why? Because as we have, I've already told that in an induction machine the magnetizing current is much more than in a transformer, because the air gap is more in an induction machine. So if the magnetizing current is more, then XM should be less. So, or you can study, you can make the changes accordingly. So this, we are talking about this stationary thing. Now, at s equals to 1, stator frequency, rotor frequency are same. Therefore, it is just like a transformer, like this thing. And equivalent circuit referred to stator will be like this. See, in a transformer, we were doing the same thing. Now, see, now see, these were the, this is, you can compare this thing to the primary side of the transformer, this thing to the secondary side of the transformer. We know that E1 divided by E2 is nothing but turns ratio in a transformer, that is equal to N1 divided by N2. But in this case, E1 divided by E2 is kW1 into N1 divided by kW2 into N2, that is equal to A. So when you were referring the secondary side to the primary side of the transformer, then you are also multiplying these resistances and these, means the X2 and R2, you are multiplying by turns ratio whole square. You can go back to your transformer notes and you can see you are multiplying by turns ratio ka whole square, A square. Then you are referring to the primary side. So this is what we are doing in this also. We are referring the rotor parameters to the stator parameters, to stator side, or basically we are referring the secondary parameters to the primary parameters, and that's why we are multiplying this A square. This is A square is what? E1 divided by A2, turns ratio. So we are multiplying that x2 with a square, and r2 is also with a square. Basically, we are multiplying the rotor parameters with a square. But keep this in mind. This thing is very important, that s is equal to 1. Supply frequency is equal to 1. We are right now, we are discussing the situation when the rotor is stationary. Then this equivalent circuit, we are deriving this equivalent circuit. Okay, things will change as soon as the rotor starts rotating, and we'll discuss about it very in depth. Okay, so you must be able to understand this thing. This is exactly nothing but like a transformer. We are transforming, or we are transferring the secondary side to the primary side. Okay, now equivalent circuit when rotor is running with some slip s. Now this is very important. Till now we have seen with the equivalent circuit when the rotor was stationary, but after this we'll see the equivalent circuit when the rotor is running with some slip s. Now this is very important, and we'll be discussing. Okay, we'll be discussing from here. We'll be discussing in your next lecture, in your next class. So I'll suggest you to go back to your transformer notes and refer those notes, and again go back to the previous lecture, video lecture also, and refer the importance of slip. You can go there, and again you can see how the rotor parameters, that is E2, rotor frequency, rotor induced voltage, rotor reactance, how does these parameters changes when the frequency, when the slip changes, when the rotor starts rotating, so that you will be able to correlate in a much better way. Thank you. We'll be discussing further in your next lecture. Thank you very much.